there, we are back. This is lesson 3, and continuing the more concept. Lesson 3. So, so far what we have found, I think utilization molar mass for basic elements. Okay, is where we were saying something like if you take a for example, its molar mass or its atomic mass is 27. It's relative atomic mass, and it followed somewhere like if you take 27 grams of aluminium, you count the number of atoms there, they will be equal to 6.0 times 10 to the power 23, and this one we found it is equal to 1 mole of aluminium, and we say that 27 grams is its molar mass. Okay, then we came to again molar mass of said if you consider something like oxygen molecules, let's say I think this one is in lesson 1, found the oxygen molecule is made up of 2 oxygen atoms joined together with a covalent bond, and with that one, if we are going to talk about its molecular mass, one oxygen is 16 in terms of RAM, so 2 oxygens will be 16 plus 16, so that its molecular mass becomes 32 grams. And this 32 grams, if we counted the number of molecules of oxygen, we found it to have 6.0 times 10 to the power 23 molecules of O2. Okay, and from there we could be able to do the calculations related to that one. And on the second lesson, we looked a bit about this one was on lesson 2. In lesson 2, we handled a bit in relation to molar masses, of compounds. And I think we said that if you have a compound, let's say something like calcium chloride, its molar mass will be calculated by adding the necessary relative atomic masses of the elements that make it up. Calcium, it's here we are talking of 1 calcium atom combined with 2 chlorine atoms, and the mass of calcium we found it's 40. The mass of calcium chlorine is about 5.5, and with this one we found it's something 40 plus this is 71, and this was coming to 111 grams. Okay, so and from here we could be able to say what that 1 mole of calcium chloride must always weigh that 111 grams, and must always contain 6.0 times 10 to the power 23. Let's call them molecules of calcium chloride or this compound. If we count the bits of that, we'll find that number. Then from here, we are trying to see how many calciums are there, how many chlorines are there in terms of atom, and also in relation to masses. Then from there, I think we started a bit on still on that lesson 2. We started a bit on the percentage compositions, which is where we continue from, and so if you haven't reviewed lesson 2 and lesson 1, have a quick view of it before continuing. Yeah, remember I said the goal is not like to complete, review and complete. Starting with lesson 1, take, if you are basically you have been performing poorly in these molar calculations, take maybe 15 to 20 minutes, whichever you are comfortable with. Every day, starting with lesson 1, day one do like only 15 minutes. Day 2 do from 1 minute 1 to minute 30. Day 3 do from minute 1 to minute 45. Day 4 do minute 1 to minute 60, about day 5, do the same the whole of it. Then day 7, 6, and 7, rest. If you are very comfortable about lesson 1, the next week you can go to lesson 2. The next week you can go to lesson 3. If you are not comfortable with lesson 1, go back and repeat the same sequence until you are comfortable. Because you still have time, and even if you don't have time, you are better off understanding part of it completely rather than rushing through and failing to get to understand it the way you need to. Okay. So, excuse me. So, continuing a bit about the percentage composition, because this one will be coming up often. Consider a compound such as calcium chloride in such a manner. Not calcium chloride, that one we already handled. Want to go with something like calcium carbonate. It looks like that. In this compound, it's made up of calcium. It has plus carbon, one atom of calcium, one atom of carbon, and three atoms of oxygen. Okay, so we want to find the percentage composition. The first thing we said is to find the relative formula mass. Formula mass of this particular compound, or the mass of one molecule of this compound. So we already know calcium. Is it 40? I think it is 40. This one I think we did check again like yesterday or another day. Yeah, it's 40 over there. It's this one. Carbon should be 12. This one you have come across it many times. Oxygen is 16. Oxygen is 16, but we are dealing with 3 oxygen. So the mass or the molar mass in this case will be 40 plus 12 plus 3 multiplied by 16. We are multiplying 3 times 16 because we have 3 oxygen atoms, and the mass of oxygen is 16. So this gives us something like 40 plus 12 plus 48. Okay, this plus this should be 60 plus this one becomes 100. Okay, these are grams. So or it's 100. Now I'm putting grams because I am considering that we are talking of 1 mole. So what I would say is that if I take 100 grams of calcium carbonate, this must be equal to 1 mole of calcium carbonate, and it also implies it must contain 6.0 times 10 to the power 23 molecules of calcium carbonate, or particles of this compound. Okay, so from here, I'm able to get the percentage composition of each element. Okay, so picking a different pen here, I want to come here and say, so I want to calculate the percentage composition. Let's say I have calcium there, I have carbon there, I have oxygen there. I want to know what is the percent composition of oxygen, of calcium, of carbon in this compound. So this one becomes calcium is 40. It contributes 40 out of the possible 100 or 100. Now this 100 there, this 100 there is that 100 there, the total mass. The second 100 is the percent. Okay, so we don't get confused by the 200 there. So the other item is carbon, which contributes 12 out of the possible 100, out of the possible 100 grams. Okay, remember when they're doing ratios, it must be in the same whatever context, times 100%. So the second 100 is percent. Oxygen contribute 48 over 100 times possible 100%. So this one I think is straightforward because 100 cancels out. and we get that calcium is essentially 40%, carbon is essentially 12%, and oxygen is essentially 48%. And your percent, they must total to 100. This plus this is 60, plus that one is plus 40 becomes 100. If you find it is either small or more than 100, then there's some a problem with your calculation somewhere along the way. Why is this important? Because then what will be the question is that if I want to make um, mm, no, suppose I have, let's put it like this. Suppose we have, uh, let's say, 120 grams of calcium. If we have 120 grams of calcium, how much oxygen, oxygen in mass and carbon in mass we require for complete reaction. Okay. So we are told given that the formula for calcium carbonate is this one, and we have 120 grams of calcium. What is the mass of carbon? What is the mass of oxygen that we require for us to have a very, very complete reaction? Okay, so that's a good exam question. Quality. And how are we going to do? The first step, of course, would be to look at let's look at our our calcium carbonate in such a manner, and we are going to say what we are going to know that in any in any compound made up of calcium carbonate, they combine in this that it's like 1 mole on one atom of calcium combines with 1 atom of carbon and combines with 3 atoms of oxygen. So I want to know if I have a specific number of calcium, like 120 grams, 120 grams, how much carbon do I require? How much oxygen do I require? So this is what I'm going to do. Let me calculate the number of moles. I'll do it in two ways. First of all, using the percentage composition, and then using the number of moles. Let's start with the one we adjusted from covering. So I know in calcium carbonate, if I have one 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 mole of calcium carbonate, I'm going to it is going to produce one calcium carbonate, 1 mole of calcium carbonate. Let's talk in moles, okay? So if I have 120 grams of calcium carbonate, what does it imply? Calcium carbonate, 120 grams. So I'll do it like this in a simple way. I'll do it like this. I know the relative formula mass for this thing. This guy is 100 grams. 100 grams of calcium carbonate or CaCO3 produces how many grams of calcium does it produce? It produces 40 grams of calcium. So if I have 120 grams of calcium, how much is the calcium carbonate, which would contain 120 grams? This one would be something, an X here. Then I will do cross multiply the same way I've just been doing in previously, and this one will give me that X multiplied by 40 is equals to 120 times 100 then divide by 40, divide by 40, and then I get my X is equals to 100 grams. Okay, so it tells me if at all I do a certain reaction and I find that I break the amount, I have a certain amount of calcium carbonate which has completely reacted. If I know that anytime I have 100 grams, in 100 grams, it always contain 40 grams of calcium. We know that, okay? In 100 grams, it always contain 40 grams. What about if, what is the mass of calcium carbonate, which will contain 120 grams? Okay, then doing multiplication, I'll find I must start with 300 grams if at all I'm going to produce 120 grams of calcium. And then when I have gone up there, then everything now is pretty straightforward because I know what I know the relative compositions or percentage compositions of the rest of the items. What am I saying? That if now I come and look at something like oxygen, I know that I need carbon. Carbon is 12%. So I'll do what is 12% of 300 grams. And this one will give me 36 grams. So if I have 300 grams of calcium carbonate, it must give me 36 grams. What about oxygen? I know its percentage composition is 48, so I do 48 over 100 multiplied by 300 grams. And so this one will multiply like that. This one gives us what? 48 times 3, 48 times 3, 24, 4 carry 2, 144. 144 grams of oxygen will be there. And as we said before, that one and that one plus that one, the three of them must add up to the 300. Otherwise, you know that there is some mistake or some problem with your calculation. All right. So that's the one way you can handle that one. That's one way you can handle that one. I want to clear up the board so that I come to the second way, or where you can use the molar mass calculation to the mole to do the same calculation. What did we say? We said if we have 1 mole of calcium carbonate like that, it must produce 1 mole of calcium, or is made up of 1 mole of calcium combined with 1 mole of carbon combined with 3 moles of oxygen. Notice oxygen atoms, it's all because of the 3 there, it's these 3 here. Okay, so we are saying 1 mole combines with produces 1 mole of calcium, not produces, is made up of 1 mole of calcium combined with 1 mole of carbon combined with 3 mole of oxygen. Okay, and then we are told that we have produced 300 grams of calcium carbonate. So I need to convert this one to moles, and from the previous calculation, you know that we used to say down here somewhere, down here, I will say something like I'll say 1 mole of calcium carbonate is equal to 100 grams. We know that by calculating 40 plus 12 plus 48, we got 100 grams. So 300 grams, how many? I want to know how many moles is that one. I'll do cross multiplication like that, and at the end of the day, I'll get my x is equals to 300 times 1 over 100. Okay, which will give me 3 moles. Okay, so this one tells me that if I have 300 grams of calcium carbonate, it's equivalent to 3 moles. So if it is 3 moles, I'm going to come here and I say, right now, I'm no longer dealing with 1 mole, I'm dealing with 3 moles. of calcium carbonate. So how many moles of calcium is it going to produce? Going to produce 3 moles of calcium. How many moles of carbon is going to produce 3 moles of carbon? I'm doing one. This one was multiplied by 3 to get 3. I'm multiplying this one by 3 to get 3. Multiply by this by 3 to get 3. Multiply this one by 3 to get 9 mole of carbon produced. So what is the mass of calcium that will be produced? I know this, that 1 mole of calcium is equals to 40 grams. What about 3 mole of calcium is equals to what? X. X will be equals to 3 times 40, which is 120 grams. Okay. I come here. I know 1 mole of carbon is equals to 12 grams. 3 mole of carbon is equals to what? X. If you do the cross multiplication, you remember, you find X is equals to 3 times 12, which will be equal to 36 grams. What about oxygen? I know 1 mole of oxygen is equals to 16 grams. What about 9 mole of oxygen? Will be equals to X. My X, so I do the cross multiplications again. I'll get X is equals to 16 multiplied by 9. I'm certain this times this. 6 times 9 is 54. You write 4, you carry 1. 1 times 9 is 9 plus you are carrying 5. This one times this is 9 plus 5 is 14, 144 grams, which is exactly what we got on the other side. Okay. So I think if you can do that, you can be able to handle most of the questions which can come up. Consider this one a little bit on the side. Um, there is a certain metal chloride, you are told, a certain metal chloride, it's called X chloride. That is the formula of the metal chloride, has has a relative formula mass of 58.5. 58.5. What is X? Okay. This one tells us this formula, going by the way it is written, it means that 1 atom of that metal combines with 1 atom of chlorine to get the metal oxide. So it means that for us to find the RFM, the relative formula mass of this, is the molar mass of X plus the molar mass of chlorine, 1 chlorine, should be equal to 58.5. But we already know chlorine is 35.5. Okay, so making X the subject of the formula, we are going to get 58.5 minus 35.5, and this one is going to give us what? Is this 23? Is it? If you are not sure, don't try to subtract the 23 is 23 grams, X is 23. And then from the periodic table, which atom has a mass of 23? Once you check, you find it is sodium, and therefore that compound should be sodium chloride. Okay, that is pretty easy. It's pretty easy. Okay, another one looks like 0.5 moles of an oxide, 0.5 moles of a metal oxide weighs 28 grams. Okay, what is metal X? Okay, uh, 0.5 moles of metal oxide weighs 28 grams. So you know that if we are going to find this one correctly, when we are looking at the relative formula mass, we look at 1 mole, not a half a mole. Okay, so I'm going to say this, that if 0.5 moles is equals to 28 grams, what about 1 mole? Because I must know the weight of 1 mole if I'm going to find the correct formula mass for that compound. And then I'm going to do my cross multiplication. I'll get 0.5 multiplied by x is equals to 28, of course multiplied by 1, divided by 0.5, divided by 0.5. Okay, and anything divided by 0.5 is like to multiply by 2. All right, if you want to go the wrong method, multiply by 10, 10 multiplied by 10. Remember, this is multiplied by 1, not 0.1. So let me do it with multiplication there. So I get here it's 280 over 5. You do long division on this one. Sorry, we are slowing you down. The some people know where first is 5 because of 25. 3, 0. And goes how many times in 656? Anyway, 56 grams. That is the mass of 1 mole. Note this, what did I want to say? That any number, anytime you divide a number by 0.5, any number divided by 0.5 is that number multiplied by 2. That's the easy. It's the same as x divided by a half, because 0.5 is a half, the same as x multiplied by 2 over 1. When you change the division to multiplication, you swap this one, do the reciprocal of this number, and you find it becomes like that. Okay, that is on the side. So we know that the formula mass, the RFM of our compound is 56 grams. Our egg or 56, our oxide is XO. So it has only 1 oxygen. So from here, how do we calculate our formula? We are saying this one, that 1x plus 1O is equals to 56. But we happen to know that O is 16, so it becomes 56. So then x is equals to 56 minus 16. So here it is like minus 16 one side, minus 16 the other side. So this one becomes 0. The other side becomes x is equals to 56 minus 16, which becomes 40. What compound has a mass of 40? It's calcium. Okay. Yeah. All right. So, having, I think having done that, we are ready to move from there. We're ready to move from here to go to the next part. Make sure you check out your books and all the materials that you can come across, and consider all the kind of exercises you can be able to come across. Okay. Okay. The other subtopic which you usually need to know very well is something which emphasizes between the difference between empirical formula, and the relative formula. Okay, empirical formula, and empirical formula is the simplest formula for simplest, not formula, but the simplest notation in which a compound can be, which shows the least number of atoms which are combined in the correct ratio. Sorry, that one is a bit confusing to define. Let's consider a product like hydrogen peroxide. Hydrogen peroxide looks like H2O2. It's two hydrogen atoms which have been reacted with the two oxygen atoms. Of course, the hydrogen peroxide is this is one of those they use as antiseptics, cleaning up the woods and stuff like that. It's one of the most unstable compound which decomposes it to become water and oxygen. Okay, so this is it's a relative formula. Okay, but its a empirical formula is I would want to divide every side by 2. I will find HO. I can put this one into bracket and show 2 there, meaning that if I multiply H2 by 2, O by 2, I'll get the same thing. So when we talk about HO, we say that this is the empirical formula for the hydrogen peroxide molecule. Okay, so this here, this side is the relative molecular formula, and this side is the empirical formula. Okay, the simplest it shows as the most basic formula for that compound, which just shows us the atoms and their ratios in the simplest form. Note, it might not be very correct because we don't have such a compound existing in nature. Okay, yeah. Consider also something like this hydrogen hydro compound. Let me pick a different color. C4H10. This is butane, I think so. So when you are drawing this particular compound, you would draw it 4 carbon atom, 1, 2, 3, 4, like that. Then hydrogen, 10 of them, 1, 2, 3, 7, 8, 9, and 10. So it is completely saturated. H, 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 H. You don't need to understand about hydrogen compound right now, but check out our site, as I said, SmartMe.Africa. We have more lessons in chemistry, and like hydrogen compounds is one of the topics which is covered. But for now, I was saying it looks like that. Okay, so if I am going to write its empirical formula, I want to divide it to make it simplest. I can divide this side by 5, by 2, and this side by 2, and I'll get C4, C2, H, 5. Okay, and then I know if I was to multiply by 2 outside, I multiply this by 2, I get H10. I multiply 2 by 2, I get H4. So again, that thing which is inside there, that is its empirical formula. Note that now the empirical formula would not be making as much sense as the real product because it implies something else. Okay, the C2 is another product which is not as which does not imply butane in any sense. All right. So then naturally you find a lot of compounds. Their empirical formula and their negative molecular formula is exactly the same. If you look at carbon dioxide, there is no any other way of writing carbon dioxide. It will be like that, so that its empirical formula, empirical formula, and its molecular formula, it would be exactly identical in such a manner, right? Why is this important? The real reason why this one is important is because these calculations assist you in coming up with uh, um, certain I mean get around certain implications or certain calculations. Consider a simple question. I think here we just go straight to the exercise so that you can see how it comes about. The empirical formula of a molecule is this one. Consider this one. The empirical formula, if I abbreviate that one, is empirical formula for a compound is written as C2H5. And these are typical exam questions, okay? If its molecular mass is 56, if molecular mass is 56, finds its molecular formula. Okay, so we have molecular formula on one side and then the empirical formula. As you saw, always we need, if we have a certain compound C2H5, we need to multiply it with a number n outside there. So there's once we use our letter n or our constant n to multiply the things on the inside, we happen to find the molecular formula, because the molecular formula is an extension or an expansion of the empirical formula. All right. So, but how do we find the n? The n will always be obtained by the molecular formula mass divided by the empirical formula mass. Okay, so that in my case, I know that molecular mass have always been given, and this is typical exam question, as I said, divided by the empirical formula mass. Now I need to find out what is the empirical formula there. Mass, it is 2 carbons, 2 multiplied by carbons, which, and carbon is 12, multiplied or added with the 5 hydrogens, and hydrogen is 1. So this one gives me 56 divided by 24 plus 5. Is that true? It's 25 plus 2. And this one is 56 over 29. And this one won't give me a good or whatever. I want to change, allow me to do MacGyver with my calculations. I think this one should have been 58, because it must give me a constant value. We have misquoted. So this one 58. So because here I needed it to give me 2. All right. Okay. Of course, in your exam, it will be something which is very exact, which has been checked. So I'll find that my formula, my n becomes 2. So that my formula now becomes C2H5. And then I need to multiply it with my n, which is 2. So opening up the bracket, I'll see it becomes C4H10. Okay, in such a manner, and you have your solution in there. Okay, consider something else here. Consider another one here, that the empirical formula for hydrogen peroxide. The empirical formula for hydrogen peroxide is HO. Okay, if the RMM, if the relative molecular mass is 34, find molar formula, molecular formula. Okay, so again, we'll be saying that the molecular formula is HO multiplied by a constant N, but N is equals to molecular formula divided by empirical formula mass, molecular formula mass divided by empirical formula mass. And what is our molecular formula? We have been given it's 34. Divide by empirical formula mass. Empirical formula mass, we'll get it from here, is a H1 plus oxygen 16. So 1H plus 1 oxygen. So hydrogen is 1, oxygen is 16. This is 34 over 2, 17. 34 divided by 17. This gives us again N is 2. So we'll come here and say HO is the same H2, HO into 2. and then H2O2, and that becomes your molecular formula for that compound. Okay, a different one, a little bit different one, but very much there. A certain compound X contains 39.1% carbon, 52.2% hydrogen. Is it hydrogen? Yes. And 8.7, is that 8.7? 8.7%, 8.7% oxygen. So it has C, H, and O with a percent with oxygen being 8.7. First of all, if I add this one, I'm going to get 100%. Let's make sure that is fine. True. 2.2 and 8.7. 10 0 carry 1 10 yeah, it's okay. This is 100 because 9 1 carry 1 10 20, yeah, carry 1 20, so that's okay. Okay, so let's continue. If the relative formula mass, RF relative formula mass is 91, what is its molecular formula? What is its empirical formula and the molecular formula? And you try and identify what compound it is. Okay, so we have a compound which contains these percentage compositions. Okay. How best do we approach this one if we know it's percentage compositions and we have the formula mass, we can be able to identify how much of each of these items are in this whatever. So assume that we have 91 grams of this compound, or exactly 1 mole, because we know that the relative formula mass gives you also 1 mole of this gas. All right, so let's first of all let's start from there. And we'll do it, we'll do this in a different way. So let's start from there. Okay, I'll come and say, should know that in this compound, carbon is that 9.1 of 100 of 91. I will know that hydrogen is 52.2 of 100 of 91. And oxygen is 8.7 of 100 of 91. So checking our calculator quickly here, let's see what it gives us. 9.1 multiplied by 1 over 100 divided by 100 equals like 5.5. So we are talking of 35.5. We'll do the approximation later. This is 35.58, almost 36 grams. Okay, what about hydrogen? Uh, 2.2 multiplied by 91 divided by 100 was 45.5. 5.5 grams. What about oxygen? Oxygen is 8.7 something like 7.9. 7.9. 7.9 grams. Okay, so these are the percentage compositions of these elements.